Hello, Math 201. Welcome to our next lecture, section 2.6 on continuity. So continuity is one of the most fundamental properties that we're going to talk about in calculus. And I don't think in this lecture we'll be able to get to all the really important things about it, but we'll get a basic idea. And so to kind of illustrate what the kind of intuitive idea of what continuity is, here's kind of a fun example from the book, or a silly example. So here's an example of two functions. One function, f of t, is the length of fish at year t. So this is a single fish, and we're saying how long it is. And we notice that at year 0, it's about, what, 2.5 maybe? And then as the years go on, it gets bigger and bigger and bigger. And we notice that there's kind of no breaks, which makes sense because the fish, as it grows in this kind of continuous fashion. It doesn't go from 2 feet and then the next year it's going to be whatever this would be, 5, 10, 15 feet, and just kind of skip all the heights in between. It has to hit all the lengths in between to get from 2.5 feet to 15 feet. I guess this is in inches. That makes more sense. 15 feet for a fish is kind of huge. So it's in inches. And so that's kind of why this function, you have to hit all the values in between to go from one value to another. So that's what the idea of kind of continuity is. As opposed to this function right here, which is the cost of a parking meter at minute t. So if you've ever used a parking meter before, you know that it costs 25 cents for the first 15 minutes. And then for every 15 minutes after, it's another 25 cents. And so it doesn't matter if you stay there 1 minute or if you stay there 14 minutes, you're going to pay 25 cents. And then the moment you hit 15 or above 15 minutes, it jumps up to the next one. And so if you stay there for 15 minutes, you'd only pay 25 cents. But if you stay there for 16 minutes, now it bumps up to the next, and it doesn't matter how much longer you stay as long as it's within that next 15 minutes. And so the price kind of has these packets, these little discrete numbers that it hits. And you notice that to go from 25 cents to 50 cents, we don't have to hit any of the values in between. There's no cost of 30 cents, 40 cents, none of that. You only hit 25 cents, 50 cents, 75 cents, and $1, so on and so forth for every 15 minutes you're parked there. And so this is not continuous, because if you try and go from this value to this value, you have to jump. There's no values in between. Whereas this one, you hit all the values in between. And so this property right here, this continuity or being continuous of a function, is a very nice property. And it's something we're going to discover. Tells us a lot about limits. This property over here of being discontinuous or discrete, sometimes is what they'll call it. A lot of functions act this way, but it turns out that they don't have about all the nice properties that a continuous function over here has. And so we say f of t is continuous because there are no breaks in the function. Another way you could kind of think about this is when you draw this function, you do not lift up your pen. You just kind of do in one continuous stroke. Whereas here, in order to draw this function, I have to lift up my pen to get to each next one. And so this is continuous. This is not continuous, not continuous. And so here's the definition of continuity. And so in order to define continuity, we need to first define continuity at a point, and then we can extend it to all points. And so continuity at a point. A function f of x is continuous at a point, so at an x value, x equals a, if the function value at that point is equal to the limit at that point. And so this was a property we said was really nice of polynomials. And so polynomials are going to be continuous because of this, because we showed that all polynomials, the limit as x approaches a of p of x is equal to the function value at a. And so all polynomials are continuous at every point. And so this property where the function value is equal to the limit value, that is continuity. So going back up to this example, every function value on here, as you approach it from the left and from the right, they go to the same thing. But this function value right here, if you approach it from the right, it goes to it. But if you approach it from the left, it does not go to it. And so the limit actually doesn't exist at t equals 15. And so therefore, it's not continuous at t equals 15 or t equals 30 or t equals 45. But any other value, it will be continuous because the limit is the same thing as the function value. And so these are the points of discontinuity. I guess technically 0, 2. Those are the points of discontinuity. And so that's the idea of continuity. So now what is or how do we check it? So how do we check continuity? And the continuity checklist has 3 things. First, the function needs to be defined at that value, right? You need to actually have a value. So if you plug in a and it gives you a square root of a negative number, square root of a negative number, or if it's 1 over 0, then those aren't things that can happen. Actually, maybe even write those. So square root of a negative or 1 over 0, you can't have those, right? You can't have those. The limit needs to exist, right? And when we say exist, we mean to say that it doesn't go to infinity. It exists and is a number, and is a number, so not infinity, i.e. not equal to plus or minus infinity. So you can't be continuous at plus or minus infinity. So if you have an asymptote, it's not going to be, it's not going to work. And then finally, but I guess this kind of is the fact that it needs to be a number is kind of implied by 3, right? That the limit and the function value need to be the same. And so all 3 things need to be true for it to be continuous. You can have things where 2 of them are true and the third is not true, or those 2 are true. And so you need to make sure that those are the same. If f is not continuous at x, then we say f has a discontinuity. So a discontinuity, going up to this example, these are the discontinuities. So x equals 15, or t equals 15, t equals 30, and t equals 45. Those are discontinuities because that's where the function is not continuous. Or we'll call it a point of discontinuity. So those are the kind of 2 things we call it: discontinuity or point of discontinuity. So what is continuity graphically? And so let's take a look at this example, similar to that example, and we're going to look at where the function is discontinuous. So where is f discontinuous and why? So it's discontinuous here because the function does not exist. It's discontinuous here because the function value does not exist. It's discontinuous here because the function value and the limit are not the same thing. It's discontinuous here because the limit does not exist. There is no limit. And it's discontinuous at 5 because the function value does not exist, right? Because it's an asymptote. And the limit does not exist, but is not a number. And it's discontinuous at 7 because the function does not exist. So 0, 1, 5, and 7, that one, 5 and 7, it's discontinuous because the function does not exist at those values, right? There's no function value at any of those values. For f of 2, the function value is not equal to the limit value, right? The limit is going to 1, but the function value is 3. And so those are not the same, so it's discontinuous. And then finally, the limit for 3 does not exist because the one-sided limits are different. And so because of that, it's discontinuous at x equals 3. So there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 points of discontinuity. And so that's how we can do it graphically. How about analytically? How can we tell when whether a function is continuous at a point analytically, meaning using algebra or using kind of numerical methods? And the way we can do that is we can see, does it exist at 1? And so what is f of 1? So f of 1, what would that be? That would be 3, 1 squared plus 2 times 1 plus 1 over 1 minus 1. But that's dividing by 0. That you can't do that. So this does not exist. So not continuous. So, or I guess discontinuous. So discontinuous. So discontinuous, continuous at x equals 1. How about the same function, but at 2? Why did I say this h? This is f. It's the same function. Is f of x continuous at x equals 2? Well, let's plug it in. F of 2 is 3 times 4 plus 2 times 2 plus 1 over 2 minus 1, which is, I have no idea, 12 plus 5, so 17 over 1. So it's 17. And then this is a polynomial over a polynomial. So the limit as x approaches 2 of f of x is just equal to, because it's not 0 on the bottom, it's just equal to f of 2. And so it is continuous, which equals 17. We already plugged it in. Equals 17, so continuous. So continuous at x equals 2. And it turns out, because we know, I mean, from before, how we compute limits of things like this is by plugging it in. And so what we're really using is we're using the fact that these functions are continuous whenever the denominator is not 0, these rational functions. And so we know all rational functions are continuous as long as the denominator is not 0. And so the continuity laws all follow from the limit laws. If you have two functions that are continuous at a value, then the following are also all continuous. You can add two continuous functions and get a continuous function. You could subtract continuous functions, multiply by a constant, multiply functions, take the power, or divide as long as the function is not 0. And so that means polynomial and rational functions are all continuous as long as the bottom is not 0. And so all of these laws follow immediately from the limit laws. And so we know a lot of continuous functions already. And we can use that fact to figure out when a function is continuous or a rational function is continuous. And so for what values of x is the following function continuous? Well, it's continuous as long as the bottom is not 0. And so it's continuous for all x such that the bottom x squared minus 7x plus 12 does not equal 0. And so which x values are those? Well, we can factor this. This is x minus 5 times x minus 2. And so that's not equal to 0. And so that means x does not equal 5 or 2, right? So x cannot equal 5 or x cannot equal 2. And so how would we write that? So continuous for all x not equal to 2 or 5. Another way you could say this, or for all x in the following intervals: -infinity to 2, union 2 to 5, union, so using interval notation, union 5 to infinity. And so that would be how we'd write it in interval notation. And we notice that we do open intervals because we don't include the endpoints 2 or 5. All right, how about continuity of a composite function at a point? So remember what a composite function is. It's when you plug a function into a function. So you plug g into f. And so here's an example of a composite function. If you have f of x is cosine of x and g of x is x squared, then f of g of x is cosine of x squared. And then g of f of x, the opposite composition, is x is cosine of x squared, or cosine squared x is how we write that. So these are not equal, by the way. These are not equal. F of g of x and g of f of x are not equal. Cosine of x squared and cosine squared of x are not the same thing. And so what this theorem tells us is that if two functions are continuous, you can compose them and get a continuous function. And so that implies that limits for continuous functions pass. So if I want to take the limit of a composite function, I can just take the function evaluated at the limit, which is just f of g of a. So here's an example. What is the limit as x goes to 0? Well, this is a composite function, f of x and g of x. We know both of these functions are continuous everywhere where the bottom is not 0. And when you plug in 0 into here, that's not, so 0, so g of 0 exists, right? And so it's continuous. So g of x continuous at 0, x equals 0, continuous at x equals 0. And so what can we do with that? That means the limit as x approaches 0 of this function of f of g of x because this is a continuous function and that's a continuous function, their composition is a continuous function at 0. So it's just equal to f of g of 0, which is, if you plug in 0, it's 0 minus 0 plus 2 over 0 plus 0 plus 1 to the 4th. And so that's going to be 2 to the 4th, which is 16. And so the limit as x goes to 0 of this function is just the function value, and it's 16. Okay, how about this one? This is a composition, right? It's the square root of 1 over x minus 1. So the outer function is square root of x. The inner function is 1 over x minus 1. But why can we not use the theorem? Well, because if you plug in 1 does not exist there, or g of 1 doesn't exist. And so we can't use the theorem. But there are some times where we can use where we can take this limit even if this doesn't exist. And so let me show you that theorem. So this is theorem 2.13, continuity of functions with roots. So assume n is a positive integer. If n is an odd integer, then f of x composed with 1 over n is continuous at all points where f is continuous. So as long as the inside function is continuous, meaning that the function exists and the limit is the same as the function, then you can take the root and it's fine. But what if n is even? If n is even, then f of x to the 1 over n is continuous at all points for which f is continuous, and the function has to be strictly greater than 0. It needs to be positive. And so, for instance, this function right here, square root of 9 minus x squared. When is that function continuous? And the way we can do that is by finding the domain of this function. The domain of g of x is when the inside function is greater than or equal to 0. So 9 minus x squared is greater than or equal to 0, which implies that 9 is greater than x squared. By the way, if you wanted to graph this function, this is the top half of a circle, right? It would be that it's a circle of radius 3 centered at the origin, and it's the top half because it's plus. Technically, there's a plus out here when we just do a square root. Square roots are always positive unless we put a minus sign in front. And so we solve for when it's equal, then plug in values to see when it's true. So if I want to figure out when x squared is less than or equal to 9, well, that's when I've solved for the equality, so 9 equals x squared. So -3 and 3 are going to be the two values I'm going to add on my little number line. And then I'm going to pick test values to see what makes this equality true. If you plug in -4 and square it is 9. So if you plug in -4 and square it, it equals 16. And so this is false. And so it does not include that part. If you plug in x equals 0, 9 is greater than or equal to 0 squared. This is true. So this part will be included. And then if you plug in x equals 4, 9 is greater than or equal to 4 squared. That's false. So we don't include that part. So the domain is -3 to 3. So -3 to 3 is going to be the domain of this function. And so g of x is continuous as long as the inside function is positive, and the inside function is positive between -3 and 3. And so you can include the endpoints or we cannot. The reason why we can include the endpoints is because at -3 and 3, the function is defined at 0. And so that's fine. And so we'll just do that. But if you were to put this -3, 3, that's okay too. So this is okay. Okay too. But whether or not we include the endpoints is fine for this particular one. And so more continuous functions. So the transcendental functions are continuous wherever their domain exists. And so in particular, all the trigonometric functions are continuous everywhere, everywhere they're defined. So in particular, sine and cosine are continuous everywhere. The inverse trig functions on their domain, they are continuous. And then the exponential functions are defined on their, are continuous on their intervals of, or their domains. And then the log functions are continuous on their domains, which remember, they don't include 0. And so on positive numbers. And so how can we use this information to figure out limits? Well, I can find out limits of something like this because this is a composition of two continuous functions. The inner function is easy to see here. The inner function is cosine of x. But what is the outer function? What are we plugging it into? Well, we're plugging in cosine x into x squared minus 1 over x minus 1. Cosine x plays the role of x right here. And so this function is continuous, and this function is continuous. This is continuous as long as it's not, x is not equal to 1, and this is continuous everywhere. And so if we plug in the limit as x goes to 0, the limit as x goes to 0 of this guy, so what we can do here is we can actually factor this. So this is cosine of x minus 1 times cosine of x plus 1. And then cosine of x minus 1. And then what we can do is those cancel, and this becomes the limit as x approaches 0 of cosine of x plus 1. And so because the outer function is continuous, and the inner function, the limit exists, right? The limit as you plug in 0 exists. Then even though this function is not defined at x equals 0, you cannot plug x equals 0 under here. You can still take the limit. And so by doing this kind of factoring thing, and what ends up happening is this becomes the limit as x goes to 0, but now we can just plug it in, which is going to be cosine of 0 plus 1, which is just 2. And so this limit will be 2. And so that's an example of some continuity that you can do with that. All right. That should be everything you need for your homework, and I'll see you guys next time.